And in this style of an overview video, I think I'll talk a little bit about the subject of gravity and try to explain why what you've accepted as a theory is so underdeveloped and immature. It's not an answer to the question, and there's a better, kind of obvious, better answer to the question of what is gravity, why there's gravity, and what makes it the way it is. So it starts with Newton's pretty much summation of gravity with this kind of a simple formula where it uses a concept of F, which is nothing that's quantizable, this idea of force, unless you put it into like foot-pounds of pressure per square inch or some other kind of mechanism. So it's really just another way of saying the energy required or the energy expended in some activity. So you can use that as a synonym in a sense. And then you have the idea of this constant G, which is just that. It's a constant, which in most cases just means he's going to come up with an answer, and it's just in the form of a number, this much. And this much doesn't mean anything unless you can convert it into this much meters per second, or this much pounds, or this much something. So you need a constant to basically take your number and make it into one of the things we already count as a way of measuring something. So it's just to fix the measurement. So it's not really part of the equation. It's superfluous to the answer. You're going to get an answer that you could say is proportional. So I'll get an answer, say, for the force between the sun and the earth, and that number might be 7,000. And if I did the earth and the moon, I'd get another number, and that number would be like 1,000. And there'd be a proportional difference between those numbers that is proportional to the fact that they are one set of comparisons is between two bodies that have a lot of mass, and one set of comparisons is going to be between two bodies that total mass isn't going to be very much. And so you don't really need this G thing at all. And the next step is to take the mass of one object and the mass of the other object and multiply them, and then this r squared thing, which r squared is the simplest part, and that's the part that's fundamental to gravity. It's the fact that the force, the power of this force to push things, diminishes by a square law, which is a cube law, really. You know, they call it a square, but it's really a cube kind of thing. Well, no, it's really a square, sorry. So it's the idea that you have a line that's this long, and then squaring it just means you make a square, and now the area is what you're counting. So like a little line, like this, would only make a little square, and this big line would make a big square. And the fact is that the area would be 4 times bigger than the twice as this. So if I cut this in half, I'll get 2 areas. Okay. And those areas by themselves will be 1/4 of how much the area of the whole thing would be. So either one of these little squares would just be 1/4 of the square. So it diminishes as you go distance by 4 times as you increase the distance between the two objects. Alright, so the problem with this is that multiplying the m1 times the m2 is you're basically saying, well, what if I just made this one tiny atomic particle? So the m is again in units of mass, and mass has to be in some sort of form, like a pound or an ounce, or a and in this case it has to be some sort of atomic weight. And so you're really talking about something that's affecting actually the subatomic particles. So it's really just about the total atomic weight of one thing versus the atomic weight of another thing. How much matter bits, how many little protons and electrons does it have in it? And so you could just convert it into a 1, and then you'd say 1 times m2, and m2, if you made it the Earth, that would give you a relationship and tell you how much force there is based on the Earth's mass to move one particle. So it's giving you a relationship. You know, how much energy will it take something as big as the Earth to move that one particle? And obviously the same amount of energy for the Sun and the Earth, except the difference is going to be is how much movement you're going to get out of that particle. So how fast it's going to move. It's probably a better way of explaining this. So the point is this force number won't be the total force experienced by both bodies. It'll be either, depending on which one you just decide to divide. You could divide by either one of these. If you divide by M2, let's say M2 is the Earth and M1 is the Sun. If you divide by M2, then you're going to find out the force that the Sun is exerting on a particle in space. And if you do the opposite and divide out the Sun and keep the Earth, then you're going to get a number that's going to be proportional to how much the Earth will affect a particle at a certain distance. And so technically this is 1/2 F if you were considering it as the total force or the total energy, because the energy is going to be yin and yang. The energy is going to come back. So it's working both ways. So the idea would be, the simple explanation is that for every movement something else moves. So when the Earth and the Sun are interacting gravitationally, if the Earth is pulled by the Sun, that pulling means it absorbed a force. That means a force that was going, okay, so there was a force, it was going somewhere, it's not going to get there because it's busy moving the Earth. And so the Sun isn't going to get hit by that piece of energy, the energy that it took to move the Earth that amount, and so that much energy won't hit this side of the Sun. So the Sun will, in a sense, be being hit by more force from one direction and less force from the other direction, and therefore it's going to move into that absence of force. But it can only move by absorbing force. So in a sense, it's going to absorb this extra force proportional to this. So it will only it will always stay balanced, in a sense, in the equation. It won't allow there to be a circumstance where a certain amount of force goes through it and a certain amount of force goes through it and those two are unequal. It's basically saying they have to be equal, and if they're not equal, I'm going to make them equal by moving. I'm going to absorb the extra, and it's going to stay inside of me. And now that force isn't going to get to the Earth. The Earth is going to be saying, where's my force? And force ain't going to show up because a piece of the Sun moved towards the Earth and absorbed the energy that would have gone to the Earth. So now Earth's going to say, hey, I'm going to do the same thing. I'm going to equal my equation, and I'm going to move towards the Sun. And again, so it's just inductive. And so the same thing, you can sort of understand your gravity, what you're feeling, in a sense, in a very real sense. You know, you're standing here on this side of the Earth, and you're saying, I'm getting pushed down. Well, you're getting pushed down because there isn't enough force coming this way. There's an absence of it. And what's causing that absence? Well, this and this are equal. Okay, so none of this matter's doing it, technically. But the matter that probably is doing it, oh, it's that guy on the other side of the Earth. See, he's getting pushed down. And by getting pushed down, his molecules are moving. His atoms, his nuclear bits are moving, and they move right through to your feet and push down on the Earth. So he's absorbing acceleration, absorbing energy. And by absorbing it, it doesn't get to you. And when it doesn't get to you, you absorb energy moving. You move. And when you move, you push down on the Earth. But more importantly, you absorb the energy, so it doesn't hit him. And you're just yin-yanging each other onto the surface of the Earth. Now it's kind of an exaggeration of reality, but in fact, that's what it takes. Any disproportions change the amount of gravity. Any irregularities. But the gravity is tiny, tiny little segments of gravity. So you can't really just measure how many mountains are below you and say I'm going to be affected by much more gravity, because the Earth kind of balances the whole thing out. So, you know, it's very big. So it gets lost in the pressure inside of the Earth. So if there's mountains on the other side, that extra gravity creates extra pressure inside the Earth, and that extra pressure is what's keeping the whole thing molten hot and all that stuff. So in a sense, it averages it out. So this isn't exactly, okay? I mean, somebody's on the opposite side of the Empire State Building, on the opposite side of the Earth, and the Empire State Building is directly through the center of the Earth on the other side. That person isn't getting pulled more, realistically. But there might be a little bit more. Yeah, maybe a little bit, but not anything we could measure. All right, so so this really isn't that complicated. It's just a simple, you know, there's a proportional amount of pulling that happens based on how much mass you have. So the more mass you have, the more capacity you have to absorb movement, and therefore absorb force. And when you do that, something else won't get hit by it, and therefore they will be moved into the absence of that pressure. So this goes back to something called Lesage gravity, or Fatio. It's the originator of it back in Newton's day. Newton did know of it and did like it for a few years, and then later, for some reason, was disenfranchised by the theory in some way or another. Hard to get details on exactly what he found to be problematic. There's no real description of that anywhere that I could find or that I have knowledge of. But that's great. It's irritating. Anyway, so I'll just read a quote from Newton, of course. You know, that one body may act upon another at a distance through a vacuum without a mediation of anything else. Okay, so mediation of anything else, you could take that to say either a substance that's moving or some kind of vibration through a substance. So it's hard to say whether he was really advocating for an ether here. But regardless, just what he's saying is basically the fact that there's nothing doing it isn't a good enough answer. And so he says, by and through which their action and force may be conveyed from one another. So he's basically saying there's no mechanism. He doesn't know why, okay, this relationship exists between something having mass and somehow it affects something else, as if it did absorb energy that the other thing isn't getting anymore because you absorbed it by being in proximity to it. Let's see. Where's the discover the? No, that's a different quote. Is to me so great an absurdity that, so he thinks it's absurd to leave this question unanswered. I believe no man who has in philosophic matters a competent faculty of thinking could ever fall into it. So, you know, he's basically saying there's nobody who thinks is going to be satisfied with this spooky action answer, this non-answer to the question, why? And I would argue that, yes, obviously conventional physics has done exactly that. So Einstein is supposed to be this great theory, bent space, bent time, all this nonsense. But at its core, all it is, well, let's understand one thing too. At Newton's time, they didn't know the speed of gravity. So, and they certainly didn't know that it might be inductive. You know, that takes a little bit of time for one thing to feel the presence of the other thing. And they start reacting to each other's existence. And they didn't know the speed of this thing because they didn't, you know, they had no clue that there was a speed. They just thought it was instantaneous. They had no way of knowing. Now later on they figured out that the math works better if you apply the speed of light. The math for all the influences of the different planets, if you do all that calculus, you'll find you get a better answer if you recognize the fact that it takes time for gravity to send its messages. So, technically the Earth wouldn't fly out of its orbit immediately if the sun disappeared immediately in an instant. The Earth wouldn't know about it for a little while, 8 minutes or 15 minutes, whatever it is. And it would just keep doing what it's doing because the force was already on its way, because it's moving the speed of light, just like light. So here, physics learned a huge clue when it learned that this force, has the same function as light. I mean, it makes it into a something, not a nothing, automatically in a sense, because it's not so spooky anymore, right? It's something more tangible, like a photon. And so that's a huge difference in terms of what you understand. Is understanding first that it's inductive, and that it's moves the speed of light. Now the inductive one they haven't figured out yet, but I'm just saying that's essentially the Einstein little add-on. But I'll try to explain. All right, so Einstein shows up and he says, I'm going to call this thing bent space-time, and the time part really doesn't have anything to do with gravity. That just has to do with a bunch of other woo, where they like to play around with these frame ideas and flying in spaceships that don't have windows, so you can't just look out the window and see how fast you're going, because you can see how fast everything's flying by. Just nonsensical thought experiments that don't go anywhere and don't have any evidence, and there's no way to prove them, and they're just of no value. So anyway, but Einstein's contribution is this idea that the space around something, they draw it in this kind of silly manner where they draw a little bowl, is bent. And bending space isn't any different. It's exactly the same thing you'd get if you just recognized what Newton was saying, which is from the center of something's gravity, you can just draw radial lines. This is kind of just Maxwell's kind of stuff too. And those radial lines will duplicate the inverse square law. So just like a sun shooting proportional lines. So it's a sphere, so it's all symmetrical. So in every direction, exactly the same amount of energy goes in every direction. And all you're really changing, so if I double the mass of this object, then all I'm really doing is doubling the number of lines. So the lines are arbitrary. I'm just saying they're a representation of the reality. And what those lines mean is they're creating the part you make a square out of. So at this distance, if you spread jelly on this or something, if this was jelly spread over a flat surface, and then back here it was jelly over a flat surface, you can sort of see that if you had a standard size spoon, that big, and you were going to try to scoop, you got one scoop of jelly you could see that you're going to get a lot less jelly if it's spread over this big surface than if it's in this little surface. If it's in this little surface, it's going to be really easy to scoop out a lot of jelly. But if it's spread over this big piece of bread, you're not going to be able to scoop off much at all. So that's the weakness of the gravity. It's just, it just gets weaker and weaker and weaker as you go further, because these lines get further apart. And those lines represent how big the square will be that the same stuff is in. So you can think of it as little dots, 10 dots. If I put 10 dots on there, there ain't too many dots. They're pretty far apart. If I was throwing darts at you and that's how bad I aimed, you wouldn't be too afraid. But if I put those 10 dots in here, you'd be more afraid, because it's obvious one of them's going to hit you. There's less chance of missing. And that's all bent space is. So that's all this is. This just represents another way of drawing the same curved lines, the same separation, the same effect. So it's, this is sort of like a topographical overview of exactly what this would look like if you drew this as lines. It's exactly the same idea. They're just converging lines, and all you're doing is representing it in a different way, but it's exactly the same thing. So all Einstein did was say, here, I'll draw you a picture of r squared. I won't do anything else. There's nothing else there. It doesn't include anything else. It doesn't say anything else. Bent space answers no questions. It just says, here's a picture of r squared made out of invisible properties. Unexplained cause. So I'll give you no cause, just like Newton, at least Newton admitted it's a problem not having a cause. And he said, it's enough that gravity does really exist and act according to the laws I have explained. And it absolutely serves to account for all motions of celestial bodies. Okay, so he says, I have not yet been able to discover a cause for these properties of gravity and from phenomena, and I feign no hypothesis. So he didn't pretend to know, and he's basically saying, but I do want to know. I'm looking for it. I haven't discovered it. And Einstein shows up, discovers nothing, okay, provides nothing. Newton could have drawn you a picture. Newton could have said, okay, let's think about it like it was bent space. It's a non-answer. It's just taking what they already knew and just drawing it funny. I mean, it's not an answer to the question in any way whatsoever. It says absolutely nothing. And here everybody thinks Einstein answered the question. It's a non-answer. It's nothing. It's the R-squared rule. It's nothing. It's nothing. All right, so the irony here is you have a perfectly rational way to look at this and say a force that would do this. Okay, so understand this force of gravity exactly duplicates, exactly the same mathematical formations are created. Okay, the same math is used when they're analyzing magnetism or charge, more specifically charge, electrical charge. Exactly the same mathematics is used, same form. A constant, charge 1, charge 2 divided by r squared. Exactly the same form. And those are describing, again, things with a force that's radiating. A light bulb would be described exactly the same way. The photons coming off a light bulb would be described exactly the same way, just change the sign. The force isn't towards, the force is away. And it's a push instead of a pull. You could think of it that way. If you gave photons momentum. So you just say, look, let's pretend the photons aren't quite as small as they are. Let's make them a little heavier. And then we could understand that they're actually pushing us. And, physicists know they are actually pushing us. Okay, you can push things with photons. They are a real pushing force. It's just a very small amount of energy. So we don't have any dramatic view of its pushing ability. But we certainly can feel the energy, the warmth of it, the heat it creates. So we know it's got energy in it. It's just very weak by comparison to the Earth's gravity. It's not a fair comparison, the little photon. But it's exactly the same formula. It's doing exactly the same thing in inverse. Okay, it's sending out rays at these distances, and between them. And it's the same inverse square law. The light does exactly the same thing. My hand, as I have shown lots of times now, I move my hand half the distance. So I cut the distance between me and the camera in half. And my hand, watch it, okay, it's going to get 4 times bigger. Can you see? It's 4 times bigger. It's really big. See? Little. Okay, 1, 2, 3, 4. Right? That's the space it fills. Exactly the same rule, right? So Einstein shows up and gives us exactly what we've already seen in light bulbs, in images, and in gravity, and in electromagnetism. Charge, let's say. And he does nothing but draw a funny picture of it. And everybody falls for it. And let's understand, when it's taught as a course, okay, when somebody's going to, when the real professionals teach gravity, they teach it as this thing. They call it an anti-divergence, which means a convergence, which means it's just energy coming from the outside. Okay, kind of obviously you could draw it this way. You could draw an anti-divergence this way, right? Because they don't want to admit that it's a push force, so they have to call it an anti-divergence. But an anti-divergence basically means there's a flow from the outside in, okay, and as you get closer, okay, to the total mass, I mean, obviously if you're outside, like if there's little bits of matter bits, and there's some way out here, they're not going to count. They're going to count against you, not with you. So the rule is you can't go inside the object, but that's a technical detail. But the real distance is from the center of its gravity. But you have to, this is what you're really counting, is this stuff here, you know, on this side, not the stuff on that side, but it doesn't matter. I mean, it's a technical detail. But it's exactly, this is exactly how they teach the subject, that there's essentially a kind of a fluid or a substance, and the substance is moving in, okay, and as it gets closer and closer, the strength, the speed of that fluid goes faster and faster, so it moves faster and faster as you know, as you get closer and closer, and everything's just floating in that, like the earth would be here floating in that fluid, and the closer it gets, the more pushing it's going to get from the river of fluid. And that's how they're describing gravity. And you know, it's clearly that's an external push force, not a pull force. They're just pretending to say, well, it's an anti-divergence, but they have no way of describing this infinite vacuum cleaner that sucks up this space stuff, and then the space never pops out anywhere. And somehow there's no where to come from, where does it go? Where the external force, I mean, you could understand, you know, that if you just concede that it has every appearance to be a push force, and that it's doing exactly the opposite of a light bulb. Instead of pushing us, it's pulling us. How do you pull us? You remove the light, okay, and you create anti-light, unlight. All right, you have light behind me, no light in front of me. I get pushed by the light, you know. So you have something that's absorbing light, and in this case, it's absorbing movement, energy to move. So when something moves, because it was pushed by an absence of force, it moved into low pressure. So when it moves into low pressure, it has to absorb energy in that direction, and that absorption means something else isn't going to get hit by it. Simple answer. All right, so so what Fadio proposed over 300 years ago, he had the right answer, and everybody just pretends it's garbage when it's you know, it's got everything, and there's only a few little you know, solvable issues, and they never attempted to solve. They just said, oh, it can't do this, so therefore it can't be the truth. And it's just such a ripoff. Drag is the real subject. So I'll finish with a little commentary on drag, but I'll do a separate video on drag. It's a non-issue. It's only an issue if you don't understand how the nuclear bits that are actually being affected by gravity actually function. That is, electrons and protons, because they don't retain permanent velocities. Yeah, it's, you know, sort of an important fact. You know, that the things move, even though the little bits inside of them theoretically don't do that. They don't do velocity in a direction on their own without being constantly pushed. So anyway, so the simple argument of Fadio's is that you have this field between two objects. There's a constant pressure. So if you make like cosmic background radiation, or even the light coming off the universe, you know, whatever, you have this force, this invisible force, invisible for our, we can't see it with our eyes, but it's just as real as a photon. It's moving the same speed. It's just as real. It just doesn't have a frequency, so therefore we can't detect it. We can't tune it in like a radio frequency. We can't tune in gravity. And so it's just this force that's pushing on everything, and it pushed the stuff together that made the planet. So the planet itself was pushed together by this constant pressure. The little bits kept moving towards each other, getting closer and closer, and as that happens, as they pile up all these little bits on top of each other, they're all still affected by gravity. They're all moving towards the center of the gravity, so they still all have some pressure pushing on them. And they certainly have the pressure on everything on the outside, so they have lots of chemical pressure. That is, my feet aren't necessarily transmitting gravitational pressure, you know, in the form of gravity. They're pushing against atoms, so it's electrons against electrons, essentially. And the electrons have all this force inside the atom, so it's the same force. Gravity is inside the atom, so I don't want to confuse you. But So it's all that chemical pressure, and that's why the interior of the Earth is molten. It's because of gravity. Gravity's doing it. Because gravity's, all this pressure is a real pressure, and it's a constant pressure, constantly affecting it, constantly. And likewise, that's why the sun goes nuclear. So when you make something big enough, okay, the pressure gets so intense near the center of gravity that everything the atoms start crushing, start breaking, and all kinds of things happen. And you can create new atoms out of all these little broken parts, and it's under high pressure. And if those atoms are in an arrangement you make and then they can survive, then they end up, being one of the 100 elements we know of that can survive. We can create lots of kinds of matter, but none of it survives, right? So that's the catch. Only 100 or so of these things are actually survivable formations. You could say more than 100 just because if you count all the isotopes of the different elements, they're obviously a little bit different. And little differences sometimes matter. So anyway, Faddeo's basic explanation was there's this ultramundane, is what he called it. Now, he didn't know what speed it had, didn't know what it was made out of, but it's just ultramundane particles, and everything's in this field of them, and he's just making the basic argument that is this object's going to shadow this object from the pressure. So here, both of these objects, the pressure comes in this way, but it's always a straight line. So just like light, it moves in rays, dead straight lines. And those straight lines mean it can't go around corners. So any force that's coming at any angle, okay, that might have hit this thing, is going to end up getting absorbed. The energy of it will be absorbed in the general direction of this, right? Especially when things are spherical, and they have to go spherical. When they reach a certain mass, spherical is inevitable because of the inverse square law. So again, it's simple law, simple rule, and this is why there's an inverse square law. This is exactly the reason. So anyway, this shadow will be exactly proportional to the inverse square law, and it's, like I said, it's just the same as light bulbs in reverse. Yeah, you can sort of understand that if I had two light bulbs and they were hitting each other and they were perfectly movable, no friction, no anything, that they would tend, the extra photons bouncing back and forth between them would tend to push them away from each other. So again, it's just the same thing in reverse for what's happening in gravity. So that was the simple explanation. Alright, now it fits everything. It fits the inverse square law. It accounts for the fact that it's moving the little bits. It accounts for the center of gravity being where the force hits. Ultimately, it's all a straight line for the center of gravity. All that equals. See, anything that's coming at a weird angle, like say something went this way through the little tiny edge of this thing, the point would be is there in a random field there would be exactly the opposite would happen on the other side, inevitably, so all of that would always equal out. All those tugs and pulls in different directions would always end up balancing out, just because of spherical symmetry. So so that explanation was presented to Newton, and like I said, he liked it for a number of years. And this was a real subject. And the problem was the thought that, well, if you do have these particles in space, then when something's traveling through space, it would end up hitting more particles coming at it than from behind it, if the particles are moving. As soon as it has motion, then it's going to be ahead of the one force, and it's going to be way behind the other force, so to speak. So one force is going to hit it more, and one force is going to hit it less as it moves through the field, and that's sort of the issue of drag. And like I said, I'll do a separate video on drag because it's complex why it's a stupid expectation, but I'll give you the simple argument, is that, see, when they first thought of this, they were thinking of actual hard particles, and so they thought about lots of problems like heat, and these little particles would break into pieces. And so obviously in the modern era, the nuclear age, we know that these pieces don't do that. Electrons don't break into pieces, and they don't do this, and they don't even ever hit each other because there's a force between them, a repulsive force. So they only bounce off of each other's fields of force. So they never really even hit each other, so they don't really have this opportunity to be broken into pieces or to bounce off at funny angles or do any of this other nonsense. But the real catch to all this is that we sort of now know that protons and electrons, red pen further, okay, both have a problem with maintaining velocity. Neither one, unless you keep pushing it with a stream of energy, okay, it stops moving very quickly. Just goes, just runs out of gas, just nothing. Okay, so you can't just throw it like a wrench into space. You can't just throw an electron into space and it just keeps going and going and going and going. It doesn't happen. It doesn't happen for the protons either. The only thing that can really do this travel, space travel, are photons, the littlest force bits. So little force bits can do it, and a nucleus of helium can do it. So this more complex thing that has, you know, protons and electrons in a formation, that can maintain velocity. You can shoot one of those to the moon, but you can't shoot a proton to the moon. You can't shoot an electron to the moon unless you keep pushing it the whole way, and you don't have enough energy to push it all the way there. A lot of energy. And so now that we know that fact, that these fundamental particles, these elemental particles, don't behave like tennis balls and golf balls and footballs and soccer balls. They don't do the same thing at all. They don't behave like a wrench or a spacecraft. You just shoot it into space, and once you get free, it's kind of a free ride. You know, as long as the gravitational influences are held to a minimum, you can just keep going and going and going, and no one will bother you. Electrons and protons don't do that. And so now we know that. We know that velocity is a little more complicated. We know it's not just things just move because they move. No, they move for a reason. There's some fundamental reason why things keep moving. Now, we don't have an explanation for why photons keep moving. I would say they're just perpetual. They never stop. They're energy. And this graviton, magneton, whatever you want to call it, all these things are made out of one force. One thing. Okay, a little bit moving. And a photon is just a little bits at a frequency, distance between them. So it's, you know, little bit, little bit, little bit, little bit at the same distance. Gravity is just little bits without any order. And magnetism is little bits in the form of electron force and proton force. I've done videos on all these subjects, so if you're curious about that. But I really wanted to just focus on gravity here. So this is a solvable problem, now that we have this little extra information about electrons, protons. Now, Newton couldn't solve it. Newton was just stuck with, yeah, that's a problem. How can you move something through a field of sand without there being drag? And if the sand is moving, wow, that's even worse. Okay, because I'm going to hit more sand coming right for me than sand from behind me. That's inevitable. So, yeah, moving sand would be really hard to get through eventually. Now the catch is here is the sand is moving really fast. So let's also understand that if there was drag, some of it we wouldn't even be able to see because it's so slight compared to the speed of the stuff that's moving. So if you're like moving 1 meter per second, which isn't a, you know, 3 miles an hour, something like that, right? 10 meters per second would be 22 miles an hour, I think. Okay, so let's say you're moving 10 meters per second. Well, let's just leave it at a meter just to keep it simple. And we know that light travels 1 meter, you know, in 3/millionth of a second. So 1/3 millionth of a second, light's travel in that 1 meter. So in that 1 meter you moved, the amount of difference is 1/3 millionth in the force you're going to feel. So it's a tiny difference in the amount of the force for that whole meter distance that you move, because you're changing so little and the force is moving so fast, so much faster than you, that the difference you're going to feel is slight because the force is moving so much faster than you are. You almost look like you're not moving compared to from the force's perspective. But obviously at faster speeds, this would start to add up to a real headwind. But again, I think that can be explained by the fact that the matter has that accounted for, and it can go upstream because of the arrangement of electrons and protons and their fundamental nature. It can essentially create a little bit of a momentum sail, a little perpetual energy machine inside of it that just keeps it moving in a direction, keeps it pushing more this way than pushing that way. A little pump just pumps along, and it's just taking advantage of trapping energy in the form of the red and the blue the black force, the electron force and the proton force, and collecting it in such a way that you have more of it going one way than you have the other way, and therefore you keep pushing forward. Alright, so I think that's probably enough. So I just want to emphasize again, this is Einstein's bent space offers no answer to gravity whatsoever. Bending the graph paper doesn't do anything. You could look at the way they draw it with spiral lines, and you could just think about it and just say, well, just unbend the paper, and that's exactly what I drew. It's exactly what a light bulb's doing. Just unbend the paper and it looks just like rays of light shooting out. And their distance apart becomes greater the further away you go. And if you square that, okay, you can understand it's 4 times more than it was here. Very not, like I said, it doesn't provide an answer at all. It's just disguised as some kind of answer. It's like it's a non. It says nothing. It does nothing to answer Newton's query, and both of his observations are left unanswered, and everybody thinks it's been answered. Everybody thinks they've solved something when they've advanced the theory of gravity nowhere. They haven't gotten anywhere. So 300 years, and they still haven't answered Newton's queries. There's problems with this. His stated dilemma of not having a medium, not having a mechanism. Einstein's is not a mechanism, it's a description of an effect. It's not a description of a cause in any way whatsoever. And clearly the second statement by Newton, that he was searching for this thing, that there has to be an answer, and he didn't have it, and we still don't have it. Because bending space is just explaining the inverse square law, which Newton already did. He already explained what exists. He could already draw a picture. Maxwell drew pictures of radiant lines, and all you have to do is understand that those lines, as I drew originally, I'll draw it one more time just so you certainly understand that all you're really doing is saying, yes, make lines to demonstrate a certain amount, a proportion of force, and this distance will tell you the amount of force you're getting. And if you increase the mass by twice, then just understand that you just put in twice as many lines. And so any way of proportionally doing that, you're just changing the distance from one known point, and that changes the distance at the far away point, and changes how much you're going to feel the force at a distance. Yeah, so I think that's probably enough. Yeah, so we'll leave it at that. But I really, where's the gravity? Had it written somewhere, right? That's not it. That's not it. What do I do with gravity? I'll put it back for the end. So, so all you people who think, Einstein did something brilliant by merely taking a piece of graph paper, spiral lines, and pulling it in and saying, look, I made a bowl out of it. It answers nothing. It says nothing, and every way it's taught as just those converging lines. It's taught exactly like Lesage gravity. It's taught as if there's an actual force pushing towards the center. That's how it's taught, and that's why they call it mock gravity, because it illustrates, it shows the effect you get, and it gives you a mechanical cause, a very simple mechanical cause. And so I don't know how any of you people can have intellectual honesty, as Newton would say, how you can have any sense of philosophical integrity, to have who has in philosophical matters a competent faculty of thinking. I mean, if you have a competent faculty of thinking, can't you see how this is not a good enough answer? Bent space, that it doesn't say anything really, and the minutia of, well, let's make a 4-decker formula to take care of a tiny bit of precession in Mercury's orbit, when most of it was taken care of by recognizing the speed of gravity, that it actually had a speed. And as I pointed out, it's basically inductive, and so that itself could be the extra little tiny bits that you need to add to the math to make it perfectly accurate for the orbit of Mercury. I mean, it's such a thin amount of mush, and for that theory, for a theory that doesn't explain, no force, still spooky action at a distance, essentially spooky space, no explanation for how the space does this, what the space does, how space could be bent, how nothing can be something, how dimensions of time can exist. Nothing. And you throw out a perfectly rational explanation that completely fits everything. It fits, completely fits very well, except for one issue, that the only really outstanding issue, which is this idea of drag, which can be explained by just observing that there's already drag. There is drag. Electrons and protons experience some kind of drag. That's why they can't keep going. So drag obviously already exists in a sense. And somehow material things, complex things, through acceleration can be reformed in such a way that they overcome the drag. But you can see that it takes a process. You can see that, acceleration is an instantaneous velocity. Acceleration is a curve. You don't get as much velocity as you put in acceleration. So you put in this much acceleration, you only get this much velocity. The velocity lags the acceleration. So clearly when something's being accelerated, something's taking place. It's not just as simple as you hit it and it goes. There's something more complicated going on. Somehow, through acceleration, it's overcoming drag. All right. Now, I can't see how somebody who has, like I said, any kind of rational parameters to, like, some kind of concept of intellectual integrity, rational good form, logic, can sit there and say this is a real contender for the truth, that science, physics shouldn't be ignoring it. They shouldn't pretend they have a good enough answer, because their answer isn't even an answer. It's just spooky space. It's not an answer. And this is so, like I said, it gives you so much. It makes it all understandable. You can I understand now. Yes, that asshole on the other side of the earth, if he wasn't there, I'd be able to float, theoretically. If the earth wasn't if the earth was solid, or if it could transmit force completely in straight lines, where it's chemistry, so it goes in all kinds of lines, so the force gets spread. So that's the real problem. But if the force could actually travel in the straight lines that it was admitted in, theoretically, the idea is you get rid of that guy on the other side of the earth and I start floating. It's that real. It's that real an answer to the question, why are you stuck on the earth? Why is it pushing you? Why do you feel like you're being pushed? Well, you are. Simple answer. All right. That's all I can do. I mean, I can't make you reasonable, unfortunately.